So, firstly, I think there's been enough hype built around this. So, I want to just dispel the myth. This is going to be a very poor, bad talk. I think it's better to lower the standards and then hopefully meet somewhere in between. Uh, but, we can start, or you want to give another minute? Okay, great. So, like Sarika said, right, we're going to talk a little bit about systems, but systems, not just software systems. We're going to try to understand a little bit of parallels around how software systems, at the core of it, every product or service out there wants a satisfied customer, right? Happy customers means a thriving business. And what keeps customers happy, right? The ability to use your product and services seamlessly, anytime, anywhere. This means your systems need to be virtually unstoppable. And that's what we call as high availability. Now let's talk about the elephant in the room, failures. They happen. Systems might go off or act up. Short-term glitches, sure, they are inevitable, and we'll see quickly in the later slides why that is the case. But what's crucial is twofold. First, creating the illusion that everything is rock solid over the long haul, and second, ensuring that when failures hit, your systems can bounce back and patch themselves up. Now, why does this illusion of stability matter? Well, as long as customers see your product, as always available, they likely overlook the short-term glitches. But let those blips turn into frequent, long-lasting outages, and you've got yourself some seriously irate customers who might just walk away. Now, on to the second point, right? It's not just about reducing the total impact. It's also about liberating humans, SREs, from babysitting duty, right? Systems that can patch themselves up means lesser frantic pages middle of the night and more blissful SREs, right? I like to call it, you get your beauty sleep well. Auto recovery isn't just a cool feature, right? It's a secret sauce to less stress and more smooth operations. Because, let's face it, happy SREs, they make the world go round. So, why are we, talking about this, and then why do we say that building malleable distributed systems is hard? Well, this is where I want to kind of draw some parallels to physical buildings, right? So, as long as it's one single floor, the building will generally withhold most calamities, right? Assuming your foundations are strong and you have basically employed good quality materials. As you start layering more floors, suddenly the surface area of disruption increases multifold. A collapse on one floor can significantly impact the stability of other floors. Similarly, in distributed systems, failures can have cascading effects. Now, there are some laws, and principles that most of you in this room are aware. I've picked the top three that I think are material. The first is CAP theorem, right? That kind of enumerate why it's hard to build systems, distributed systems that will not fail. CAP theorem, the part that's most interesting here is the P, right? The network partitions, which are a given. They will happen, right? You cannot live in a vacuum. Partitions are going to happen. The next one is the Amdahl's law, right? Which is interesting because it says you can scale your systems by parallelizing them until a point where you reach a serial point of contention, right? So there is going to be a limit to universal scalability. And the last one is my favorite, which is Murphy's law, which says anything that can go wrong will go wrong, right? And so if you have to kind of start thinking about building systems, building malleable, resilient systems, keep Murphy's law in your mind all the time. And so effectively what I'm saying at this point is there are no guarantees, folks. And you're kind of beating yourself up and saying, waste of time, don't know why we have come to this talk, right? So, well, let's pause. So the good part is that while the solutions are custom made to our domain of computing and engineering, we can take solid inspiration from some core principles of structural engineering, which date back to 2700 BC. Now, what is structural resilience all about? So, it is the ability of a system to withstand and recover from disruptive events, shocks, while maintaining essential functions, integrity, and performance, right? So, keywords, which is you do not need to be fully up, but you need to be up enough so that you can maintain your essential functions. And related to this is the concept of malleability in material design. And what is malleability? It is a physical property of a material that allows it to be deformed under pressure without cracking or breaking, right? Now, hopefully you can kind of start to think about how this relates to software systems, right? So you could build systems that can bend, that can possibly get as close as to their, disruption point, but they don't actually crack, right? And in these two concepts is basically where the beauty of building resilient software systems lies. Now, structure resiliency and malleability are a pair made in heaven, right? And we'll see three properties of malleability that lend itself beautifully to structure resilience. The first one is the adaptability to dynamic loads, right? Structures, when they're in dynamic environments, they benefit from malleability. The ability to deform temporarily under stress enables the structure to adapt to varying loads and the ground movements without actually suffering some damage, right? Again, back to the concept, malleability allows you to distribute the stress without actually cracking. The next one is post-failure integrity, right? In situations where failure is inevitable, rather than a sudden and complete collapse, a malleable structure can have some load-bearing capacity and some deformation, which gives you enough time to evacuate the situation, right? And that's again very crucial, right? Rather than reach this point where everything is just collapsing, you get some breather in which you can replace and you can evacuate. And the last one is ease of repair. Malleable materials allow for easier repair and retrofitting. After a stress event, structures can be restored more effectively because the material's deformity allows you to reconstruct it without having to stand up the entire building again. Now, if all of this has gone above your head and you're like, what is this guy smoking? We'll come to it. And I promise I'll kind of try to tee this up, on how it impacts the software systems. Okay, so before we dive in and talk about how to build malleable software systems, I want to make a very critical call out, which may be often overlooked. If you're a product or service that may occasionally cater to high volumes of traffic, which we typically call as large-scale events, the way you'd want to think about your malleability for those events would be very different than how you think about your BAU, that is business as usual. This sounds like a bit of an entire pattern, but we'll deep dive into more on this in the later slides. Now, we have this bit settled. One of the problems I often see engineers grappling with is how much resilience should I build into my systems, right? Do I cover every possible risk scenario? Do I cover the top 10 as articulated in some YouTube masterclass? Do I see how large organizations build their systems and that get inspired from them? So what I want to do today is to help you all build some intuition about how to incrementally build malleability into your systems and architectures. So in line with our theme for today, let's go back to building a house from scratch, but we are not civil engineers. Okay, so let's build some products and businesses instead, right? Cool. So we'll start with a product that we believe has a potential disruption value. We're in the product market fit phase. We start off with some microservices thrown here and there, some databases, some caches. We also put some Nginx HA proxy, and we get the ball rolling. Early feedback tells us that customers are loving it, man. Like, they're all crazy for the product. And the product team comes back and asks to add more features, right? They say delight the customers and ship new stuff each day. This starts the positive feedback cycle, and customers start to come in larger numbers. You start to scale more. Suddenly you find the number of microservices have grown to 10x. Your local data center cannot handle your traffic anymore. So you move to K8s, you move to cloud. You're doing everything by the book at this point. Until one fine day, things start to fail, right? You don't have the time. So your immediate reaction is to add more servers, scale things up. You add more caches, more services, more database shards. You're now firefighting every other day. Patching systems one at a time until you figure that you must slow down on your development and go back to the board. This is largely because stability and resilience wasn't your key concern up until now. So how could we have done this better? The first thing to do is to clearly define and identify the criticality of each of your systems. Now, these systems could be a single service or a set of services that work together to serve a user function, right? So you start with some definition of critical versus non-critical, and this will be basis the product and the domain that you're operating in. And with that lens, you start looking at each of your systems, right? Now, note, I am categorically saying system, not services, right? So you have to look at a set of services that possibly come together to deliver value for a single customer function. As an example, login. Login is not one service, right? There's the login front end, there's a login back end, there's going to be analytics, there's going to be events, there's going to be SMS providers. That is one system, right? So with this definition of some P0s and some P1s, you'll start to delineate. But what is P0? So your P0 components are the ones that are in the path of serving a critical customer promise. Rest everything could be P1, P2, P3, doesn't matter, whatever non-P0 tag you give to it. Your key focus should be to ensure that your P0s are up as much as possible. Now, going back to the case of the OTT app, the current domain that I work with, our key priorities are first and foremost that the video must play at all times, right? This then allows us to shortlist everything in the path of user opening the app to reaching the actual watch page. Now, rest of the stuff like search, event analytics, they can become non-P0s, right? We can turn them off, or we can keep them alive on best effort basis. Now, again, this does not mean that you don't care about the uptime of your non-P0 components, right? That's not the idea. It simply means that when you need to make hard prioritization calls, which could be either in your planning phase, in your sprint planning, which could also be when you're in the midst of an event or an outage, you will need to prioritize to keep your P0 components on. You need to bring back your P0 components back first, and only then move to the non-P0s. Now, once you've identified your P0s, how much and what kind of resiliency should you bake in? The simplest one is to check the call patterns of your P0 components. If it is doing more than one kind of a workload, simply decouple them. Don't think twice, don't flinch. It cannot get easier than this to add resilience in a P0 system at an early stage. Either separate them as two independent services or deploy them as independent units with their own databases and caches. This basic level of tenant isolation will ensure that the two disparate use cases never overstep on each other. For example, in the case of our OTT platform, we started out with a single deployment for our BFF stack that used to power the entire app experience. Now, pretty soon we learned the hard way that even minor blips in the homepage code could actually lead to bigger issues in the watch page experience, right? And by federating the two, we could now stagger the changes more effectively and test them on the home page for a longer period before we get them out to the watch page experience. Another simple check to look out for is the code paths and design choices where you might be doing unbounded computing. Use basic tools in your armor like pagination, capping execution time, limiting thread pools. This is to make sure that you never brown out by excessively trying to serve expensive requests, right? Now, if you think about these are not tough. These are not time consuming, right? You just identified your P0 systems, and as you're coding, as you're design reviewing them, these are simple checks to just build and execute upon. So, 1 second. Right. The next one is a basic implementation of concepts like timeouts, exponential backoffs, jitter retries. I don't want to go into the depths of these, assuming all of you understand, why these must be done. But don't go super fancy. And okay if you don't get these values right from day one, but make sure they exist in some form and shape. The one I recommend the most is to have some form of rate limiting, right? This is honestly a topic that's very close to my heart. And I think over the years, I've kind of learned why this is such a beautiful concept and how much resilience this single act can add to your systems. To understand this, rate limiting is actually a lever to improve goodput, right? Now, what is goodput, you may ask? So goodput is different from throughput, right? You may be doing tens of thousands of requests per second. But if half of those requests are just failing, erroring out, right, or timing out, then your throughput is effectively zero, right, or is down to the ground. You're much better off doing only a few thousand requests, but the ones you do actually serve meaningful value to the user, right? They actually allow the user to interact with your app, to use your product more effectively, right? So this rejecting excess traffic is therefore a very, very good option for your early stage services. It also allows you to build a feedback loop where based on the number of rejected requests, you can actually tune your auto scaling policies. So remember we spoke about keeping your pages low in the night. This is a very beautiful feedback loop system where the system can start to auto heal the moment it determines that I'm rejecting a request beyond a certain threshold. So let's say we do all of this, right? What do we really get? Firstly, with these simple measures, you can now ensure a reasonable uptime for your P0 services. As more customers and features get added, your P0 components will generally hold well and maintain a steady performance profile. On a larger level, it allows you to start bringing in some SRE discipline to your organization. You have now suddenly matured from being a team that was just focused on shipping code to a team that actually is owners of a steady performing systems, right? You can use this initial phase to also bring company-wide standardization of best practices and templates. Finally, your product can now promise goodput to your customers in most cases, right? Remember, it's most and not all, since we have just handled very basic scenarios. It's like protecting your house from torrential rains, but not yet tsunami secure. Next, we enter the crazy growth phase of the product. Now, in this phase, we are adding more functionality to our product. Take, for example, again, back to the OTT app, a simple login workflow. What may have started off as a very simple login button with basic auth is now becoming a federated login page. You now allow users to log in using their social handles. You also support OTP and IVR as the authentication options. You also want to know if your login success rate is beyond a certain tipping point, so you add more levers, you're listening to callbacks from your SMS providers. So you get the drill, right? And you're now going to observe a lot more failure modes which were not there in the system before. Your deployments are also going to start throwing in surprises now, right? You suddenly observe that your pods are doing just about half their original throughput, right? You're getting paged more often because your pods are crashing, and your rate limiting isn't helping either because clearly the thresholds have gone for a toss. And you go back to the mitigation loop by scaling up, scaling out, but in this phase, throwing money is going to hurt your balance sheet a lot more. So now that we are in this phase, we need to start dealing with this at a little more deeper level. Now remember we spoke of isolating call patterns in the phase 1, right? In phase 2, you need to do this all over again. Now this is because as the org and product evolved, you probably added a lot more functions and flows to your components that again brought varying use cases together on the same set of services. This time you have to also start looking for shared dependencies upstream and downstream. So while you may still have two different deployments of the service, you're probably still sharing the same endpoints of a dependent service. You're on probably the same network. The pods are probably landing on the same host machine. A very effective technique to mitigate some of these issues is to move to a more formal means of isolation, which we refer to as cell-based architecture. Now, this is a widely known design pattern where you create multiple replicas, aka cells, of your entire call stack, and you route a group of customers through them. Now, this ensures that the isolation unit flows through the entire stack and not only limited to your one single service. I think Radhika earlier did a detailed talk on this, so I'm going to skip all the gory details. Now, note that this comes with a fairly heavy orchestration cost, right? You have to manage these cell setups, you have to manage their deployments, you have to manage their observability very differently than versus what you would do for a single service. So pick it if you must, or better yet, I recommend you do it only for no more than top 10% of your P0 components. At this stage, it also becomes critical to introduce some formal means of regular checkpointing. Now, deployment workflows are a very cheap lane to get onto. So start off by introducing a basic canary setup in your deployment pipeline. Don't worry about monitoring every metric, right? Start with the top 2-3 resources and observe deviations on them. Bonus, if you can integrate some off-the-shelf anomaly detection engine and check for short-term and long-term deviations. Any change that seems to have impacted the service profile beyond an acceptable threshold must be rolled back and patched, right? So here, the discipline part is way more important than the doing part, right? Because until you induce that organizational discipline to say we cannot have performance regressions, you are not going to be successful in the long run. The third one is a bit contentious, right? And this is fallbacks. So firstly, let's see what do we mean by fallbacks, right? In the simplest example, and back to the OTT app example, on the user homepage, right? This is when you're kind of opening the app and you see a bunch of titles up and down. We show these titles that we think you would like to browse, right? Now the system that is generating these recommendations for you, because it's a personalized home page, that could go down. So now rather than show you a blank error page, right, we could temporarily fall back to a pre-generated home page with some titles that we think largely work for most users, right? So I could show you a top 10 titles in India right now, right, which I think may be valid for most of you. So what this allows is the user to browse and hopefully still find something to watch rather than stare at a blank error page. A more elaborate feedback could be where, say, the search engine tries to look up for some query, say, in a Leucine index. But if the index is unsearchable, it decides to fire a query on the underlying database. Now, this sounds like a fallback, but this can actually cause more damage. Right? This is one of the reasons why I personally hated fallbacks for a long time, because they violate a lot of the core design principles of constant work pattern, and they bring multimodal behaviors into the system. To give you a little more glance into why fallbacks are potentially dangerous, going back to our civil engineering, imagine you're a building constructor and you build this magnanimous apartment complex, right? And you're a thorough builder, so you thought, let me get the electricity lease line from the municipal council, but you also were able to foresee that these lines may go off at some point in time, someday. So you added a power backup generator, right? Now comes a day when suddenly the power lines are indeed blippy, right? So your residents, they show no sign of distress, right? One of them quickly goes and says, let's turn on the backup, we'll do the magic. And boom, the entire apartment is now staring at a large scale outage because this damn backup was never tested in the last few years, right? It had worked well 2 years ago when there were probably 100 residents in the apartment. But suddenly, as you grew from 100 to 500 residents, the backup wasn't able to sustain and it took away all the fuses and tripped the entire power. So the key lesson is build fallbacks, but exercise them as BAU. Right? Make sure that a part of your traffic is always getting routed through the fallback flow, and that under no circumstances would that volume change drastically. Remember, less exercised code path can cause way more damage, and this is where fallbacks can hurt you more than being a savior. Also make sure that your fallbacks aren't trying to be as fancy as the complete service response, right? You should return the minimal bits in the fallback path just to get enough done. Right? Back to our example of the homepage, you don't have to return every bit about the content. You don't have to say whether this is in the user's watch list or not, when did the user last like it or not. As long as you just show some titles, the user can browse, and this is a temporary fallback situation, you're good. The final one, which is often overlooked, and again has been a heart of many outages that I've seen over the years, is a non-P0 component in the path of a P0 component, and that leads to brownouts, right? Make sure once in every few months you conduct this simple exercise where you turn off all the dependencies of your P0 systems one by one, and then check whether your systems can continue to come back up or not. If they cannot, then you ask yourself why that is the case, and why the system cannot run in a degraded state without that component being available. Then also go on to check that the system restores to full functionality when that component comes back up. The number of components that must be truly available for a P0 system to serve the minimal functionality must also be P0s themselves. Right? Now, here again, I have a very simple example, and that kind of tees up both the pitfalls of fallbacks, P0s depending on non-P0s and stuff like that. So this is a scenario where in one of our services, all of a sudden we had some service endpoint that they used to call at the boot up. And as luck would have it, that endpoint was unreachable for a certain duration of time, right? Now, the service owners had very beautifully planned a fallback to say, okay, we'll go to S3 and we'll fetch some static data from an S3 bucket, and we don't need this endpoint. Now, guess what? The auth policies for that bucket were revoked. So now you had a P0 service, which had this P1 dependency, which was failing. They had a fallback to S3, which failed, and the entire P0 service was out, right? So again, demonstrates the point that a non-P0 dependency or a poorly done fallback can bring down your entire P0 service. So be cautious. Okay, so we have done some heavy order business. We have basically now added more girth to our structure. We have tried to patch some more vulnerable points. Where does this lead us? First, We should now be more available than before, clearly, right? Fallbacks will ensure that in most cases, users get at least something meaningful that keeps them going forward. The bigger win is that even if now one of your P0 components starts to embrace these practices, it goes a long way in building the organizational muscle memory on how to implement these to other parts of the organization. Now, of course, you're still not 100% patched, right? And unless you are in a very crucial sector where human lives are dependent on your product, don't aim for 100% coverage either. Remember Murphy's Law? Unless you're aiming to be the next big cloud provider, you're always going to hit shared fate with some undersea cables, DNS, flappy routers, data centers, cosmic rays. You get the idea. And so, you can keep iterating on phase 2, covering your bases one after the other, until you get to the point where you feel reasonably confident that your systems are generally malleable. A good indicator would be to look at the metrics around the number of incidents that you're getting week over week, the amount of times your people are getting paged, the number of times you're rolling back deployments, and other good observability metrics. Now, this is largely the end of the BU resilience, right? I've omitted a bunch of details and patterns, by the way. We did not talk about stateful components. We did not talk about data center redundancies, async systems, queues, networks. So in no way should you treat the past slides as exhaustive, but just use them as a framework of reference to determine how to incrementally reason about vulnerabilities in your system design. Now, all of this works for traffic patterns that are predictable and within a formal range. If you happen to be in the business of supporting and preparing for large-scale events, the stakes are simply another level, right? So what are large-scale events? Large-scale events are typically what you observe with platforms like e-commerce, OTT, fintech, where an inorganic flux of customer traffic is driven to your products and services on the back of an exciting external stimuli. Typical examples are shopping festivals on Amazon and Flipkart, and something closer like cricket tournaments like World Cup in a country like India. And this is probably the bit that most of you are attending this talk for, and my sincere apologies for having taken this long to get to the point. But before we dive in further, let's look at some characteristics of these large-scale events, right? So what is special about these large-scale events, right? You'll generally see very, very high footfalls on the platform. They'll typically come in a very short period of time. So these are very busty loads, right? You'll have millions, billions transactions per second, so you get the scale magnitude. Your brand image is under constant scrutiny at this point, right? Every customer is on social media saying the site is not working, I'm not able to check out, I'm not able to watch, right? And customers' expectation of performance and availability are skyrocketed at this point, right? If you think about this, on a regular day, customers would easily ignore these failures, right? They'll probably retry, they'll probably come back after 5-10 minutes. On these events, that is not the case. They want it working every damn second of the day. So if one fine day, I come to you and told you that your product, which used to handle, say, 1000 RPM on an average, now has to prepare for handling 1 million RPM. How are you going to react? Hyperventilating? Okay, calm down. Let's take a deep breath, right? This is not a made-up scenario, by the way. This is almost how our OTT platform embraced the challenge of preparing for an upcoming large-scale tournament, the scale of which was going to be unprecedented for India, let alone our systems. Furthermore, this was going to happen on a tech stack that we had re-architected an year ago and which hadn't seen even a mid-level tournament to prove its scalability. It's almost like exposing a newly constructed skyscraper to a hurricane before it had even the chance to withstand a mild tropical depression. So we braced up, right, and we went back to the basics. Simple rules that we had learned in our BAU implementation, they continue to be our guiding pillars. What are those? Goodput, fallbacks, and minimum moving paths. So we've spoken about the first two, but minimum moving paths are basically analogous to reducing the amount of wear and tear on your system, right? The lesser the number of paths, the fewer failure points, and better malleability. The one new thing that we did this time was to let off whatever we knew about the systems and BAU patterns. This is a very powerful technique that I encourage each one of you to employ once in a while. We asked ourselves if there was any silver lining in this ginormous wave of traffic that we were going to prepare for. Interestingly, we quickly discovered that user behaviors and expectations from the product are very different on these large-scale tournaments versus BAU. And armed with this knowledge, we went on to figure how to exploit this fact for our scaling strategy and to build newer layers of malleability into the system. To help you build some intuition around this, back to our theme of buildings for the day, Now imagine a typical nightclub in Bangalore, right? On regular days, you'd have customers dine in, spend time deciding their drinks, and occasionally hitting the dance floor, right? Probably towards a late night. The floor plan of the club would be to carve out ample space for fine dining and a smaller area dedicated to jam. On peak events like New Year's, most customers are actually hitting the floor, right? They're quickly ordering their drinks at the bar and rarely settling in. It therefore makes sense to redo the floor plan on those days such that the dining experience be given a much smaller footprint, and the larger focus is to ensure that the party vibes don't get disrupted. So be the outsider, look at the peculiarities of your traffic patterns on these events, and then figure out how can you leverage them. Great. So we went back to the drawing board and we made some broad stroke decisions. First one, we could not fool ourselves to believe that every single piece of our product would continue to work pitch perfect and be utilized at 100% efficacy during the peak events. We worked with our product and business leaders and we zeroed down on the most critical experiences and workflows that had to be kept up and running. For example, the watch page experience must be served at all times, even if, say, the home page was partially broken. Even for the ones that had to be kept on, we further identified which ones of those are truly differentiated and must be served in near real time. For example, even in the watch page, the player and the video streams must be served at all times, even if we temporarily had to take away the ability to switch the stream qualities or languages. You allow the user to at least watch some stream in the worst possible case. The partnership with product and business is extended beyond P0 scenarios, by the way, right? And we deeply work through them to identify their expectations and needs from the product during these events. For example, are we planning to run any offers? Are we going to send push notifications to the user, right? At what times would we want to send these notifications? Again, in these smaller decisions, we were able to help our business team empathize with the tech stack and then make modifications. For example, we made a change to our push notifications where we started to stagger them versus bringing them all one shot, right? This allowed us to spread the traffic spike over a larger duration window versus bringing it all in. At this point, we were potentially looking at re-architecting a stack that we had just built over the past 1 year, right? It was a hard pill to swallow at first, but then we understood some critical lessons as we made peace with this fact. First, these patterns and trade-offs are something that we could not have anticipated, right? No matter how hard we tried. And we could not have aligned stakeholders on these shortcuts either if it truly hadn't become a reality. In fact, we'd have violated the Yagne principle had we gone about architecting these before these actually became real. Multimodal behavior is something that I spoke about in our discussion for fallbacks. This is something that I personally, I'm very skeptical of. But in this case, we had no choice but to embrace it. We took a conscious call to move on with this. We decided to fork our stack in a way that it would be very tailored for high velocity events, and that eventually we'd find a way to fold some of these back into our BAU designs. It was extremely hard at first for us to reason about the failure modes and plan for them. We attempted a bottoms-up approach, right? We asked each service, each component to say, go back, write down how all your system can fail, how are you going to recover, what bullets you're going to fire. Right? We had a pile of documents that could describe the system behavior down to every bit, but did not help us understand the user experience when those failure modes actually occur. So our product leaders could not empathize with us. They could not tell us whether this was acceptable or not. So we stepped back and we did a top-down and outside-in approach. Right? We listed the key customer journeys. We spoke in terms of broad failures. Right? Instead of saying this API fails, that API fails, we said, imagine network goes down. None of the APIs in this path are working. Right? What would be the user experience and how do we want to deal with it? On the same lines, we also decided to ditch fine-grained fallback levers and instead solve in terms of broad stroke fallbacks. Now, while we were figuring out how to be malleable in the wake of this traffic avalanche, we were also grappling with some physical world limitations. Our back of the envelope calculations showed that we were soon going to hit the hard limits of physical hardware and virtual layers. K8 cluster limits, EC2 node and network limits, IP range limits, you name it, we had it. And as this wasn't enough, we also learned that at our scale, we'd possibly start eating into most of India's active internet bandwidth. The CDNs themselves were going to hit limits of I/O and compute per node. Now, as they say, Paucity leads to innovation. We again took this as an opportunity to step back and identify ways in which we could handle this. Our first insight was to evaluate whether all the traffic must be brought to our data centers and origin services. We identified the most critical traffic that truly must be routed in, and we decided to deflect large amounts of non-critical traffic to the cheap edge nodes. For example, we must authenticate our users and we must give them a video URL basis their entitlement. Now, this is something that truly needs to come to the data center. But for showing the image of the content, its rating, its description, right, this is something that we need not do a deep check with the origin all the time. This is something we could just offload to the edge nodes and have them periodically refresh on. In order to bypass the limits of the CDNs, we took the learnings of our cell-based architecture and sharding, and we came up with some innovative solves to dynamically load balance traffic across CDNs while balancing the customer experience and still honoring the upper cap limits of our CDN partners. Okay, so we started to re-architect our systems, for this large-scale event. We also had to make sure that our P0 systems were still resilient. Now, this may sound like a bit of a conundrum, right? Like you had plans, you had fallbacks, you said traffic will not come to origin services. Then why are you still worried about your P0 services? The answer lies in Murphy's Law, right? This was the first time our stack was going to see this kind of a surge traffic, right? There were new user journeys that were introduced. The client apps were brand new. We had prepared for most happy cases, but there could be all kinds of subtle bugs, untested code paths, unpredictable user behaviors that could surprise us. We could not risk going in unprepared for these scenarios. To tackle this, we spun off a formal tech assessment of all our systems in order to certify their readiness for malleability. This is more commonly known as service audits. It is essentially a detailed questionnaire that we ask each of our P0 systems to fill in. The process begins by the system owners firstly going back to their architectures, reassessing which of their components are again P0 versus non-P0. Once the tagging is finished, the service owners start by filling a detailed questionnaire. The questions go very deep into every aspect of the system, right? They range from scaling policies, timeout values, through the funnel, your caching behaviors, load balancers, etc., right? This questionnaire is then checked and verified by a senior engineer from another org. This allows for a neutral assessment from someone who doesn't carry the baggage of having known the system in depth and encourages some probing. Finally, from the CTO's office, we conduct a random audit of a handful P0 systems, where a council of engineers handpick some audits and check for quality of work. This is really a trust but verify process if you think, and it ensures that a min bar is maintained throughout the organization. At the end of the exercise, the system captured their open risks in a risk register. Each risk is tagged as SEV1, SEV2, SEV3 depending on its possible blast radius impact. And we ensured that going into the tournament, all 7 risks were addressed and that the SEV2 risks should be minimal in number. Okay, so we're now at a point where we have technically written all the code, we have strategized on paper and stuff seems to work, but that ain't how we get to the field, right? We need to test whether stuff really works the way we want it to. In this case, it's all about the scale. So clearly, we needed to conduct some game days. We need to simulate the production-like workloads in some environments and figure out the breaking point of our services. Fair. But for that, do we know what the expected traffic is? Sounds like a simple problem. Unfortunately, it isn't. This is a critical step that is very core to the degree of confidence that you can build on your stack. You estimate more, you probably are going to spend insane cycles trying to optimize your stack for patterns that you won't even see in production. You estimate less, and you're basically sitting on a ticking time bomb. So your best bet here is again to partner with your product and business and lean in on the past patterns, if any. So we did exactly that. We worked with the finance and growth teams to just understand the traffic projections that they had created, the mix of traffic that was expected. For example, how much traffic do we expect from mobile versus how much do we expect from TVs? This was important because the API calls and the video qualities for the two device types are very, very different. We then worked with the product teams to understand the user experiences, right? What steps would you expect users to go through in each of these platforms on an average? How many scrolls do you expect there per page? What parts of the page do you think will be personalized versus non-personalized? And so on. Basis all these inputs, our architects created a journey level funnel, and by exploiting the knowledge of what downstream calls each part of the funnel makes, we arrived at some ballpark numbers of traffic that were expected for each of our P0 systems. We also created worst case projections to accommodate some error in our projections. Right? Each team lead then validated the math and they were able to adjust these numbers should they have more insights. With this base work done, we now proceeded to create a production-like setup in our load environment. We created a clear set of tests that we'd run the game days on. Apart from standard load test, where we just generate synthetic traffic, we also did tests to figure out if our K8 clusters can even scale up in these large numbers without hitting any limits. How do the systems behave when, say, a large number of load balancers go down? We observed the readings from each of these systems, and each anomaly was raised as a SEV1 or a SEV2 risk until it was fixed and retested in a subsequent game day. One of the realizations that we had was it was crucial for each team to have access to our load scripts so that they could replay only the part of the traffic that was relevant to their systems in a vertical load test. Right? The cost of doing a coordinated org-wide game day just to realize there's one flappy component that's going down all the time is exorbitantly high. Right? And so it's a lot more prudent to have each of your systems validate, pre-certify themselves in a vertical load test before you come to the coordinated game day. Cool. So we're now ready to take on all the load that comes our way, right? But wait, we still know that failures will occur, right? We know that as stuff goes crazy, we must have ways to move traffic around or to turn off non-critical features. Remember, video must keep playing. Now, human minds, they work in mysterious ways, right? When things are going fine, each brain is working at 100%. As soon as shit hits the roof, there's paranoia, there's confusion, there's chaos all over, right? Suddenly you are in a war room with 100 voices speaking over each other, right? Everybody's scrambling to find answers to help save the day. This is where all the preparation goes down the drain. So the simplest answer here is to rehearse so much that the final day feels like just another day. Muscle memory, you see. We organized a set of mock drills where we'd artificially inject failures into our load environment and have the engineers pull the planned degradation levers. We of course didn't get it right in the first drill, but by the time we exited, we had nearly perfected the SOP. We were now clear on what each lever gives us in terms of the headroom, what's the right time to act upon it, who is the Spock who will execute that lever, and so on. Likewise, we also practice the discipline of running the war room. We have a very detailed policy on how the war room is run and managed. An anointed game marshal calls the shots on everything and is the sole authority who can override everyone. The marshal is assisted by individual team on-calls and all tech and product leaders, but this ensures that there is no confusion on who will make the decision. We also tested for hygiene around how to page the on-calls, how they should respond and act. We retested our dashboards and ensured that they had all the right information and that even somebody external to our systems could get a 10,000 feet view of the system health. And with this, with months of planning, execution, testing, and rehearsals came to an end. And the true recognition of success was when our systems were able to withstand all kinds of storms, typhoons, hurricanes that came swinging at us. We stood tall, bearing it all on the back of our strong foundations, and with the help of our malleable structures that were able to bend, deflect, but never crumble under the stress. So at this point, I want to quickly recap some of the key learnings from our journey and a quick rundown of what I tried to cover today. Firstly, your structures are going to be only as solid as your foundations. Make sure you invest reasonable time in strengthening your P0 systems over and above everything else. You don't want to ignore basic hygiene here. 2, don't aim for 100% coverage from day one. Let the systems evolve. Let the usage patterns evolve. Learn from them and incrementally patch. You know the tools and you own the toolkit. Figure the right time for the repairs. Every leaky pipe, every shaky nail does not demand your attention right away. Third, you must embrace chaos and build for being malleable. It's always better to bend than crack. Let the stress spread out, then spread in. Reject load to maintain goodput and build systems that can come back to their normal selves once the storm has surpassed. 4, you may often lose the opportunity for simplification and building malleability from a customer use case standpoint if every floor is built in isolation. Appoint architects who can look across the floors. Bring these builders together and understand how the entire unit comes together, and then build the resiliency for the residents. The sum is greater than the parts. Number 5, don't confuse yourselves to believe that your BA resilience will sail you through a large-scale event. The two are very different ball games. And while the principles are largely the same, the implementation choices will drastically vary. And lastly, don't try to solve for malleability in isolation. It's a shared goal and responsibility. In the end, you're doing this for your customer, so create a shared goal around this. Seek inputs from your partners. Learn and rehearse ahead of time so that when the time comes to pull the chain, you are able to do it even if you're in a deep slumber. And that's my time. Thank you so much.
Thank you so much, Harsh. We are slightly over time, but we can take maybe a couple of questions. So if you have questions, please come.
And unless you're already asleep. Please.
Hi. My question is about feature development and resiliency testing. Is there how do these get scheduled? Like, is there a phase where the feature development stops and then resiliency testing happens, or is there some kind of automation that you've got? Like, how do you schedule these two parts?
So again, I think the answer is on the what phase of product development you are in, right? So like I said, in phase one, you do not actually do a formal resilience testing as a product development phase or a part of the SDLC, so to speak, right? Which is where you kind of build the broad strokes to say, okay, if I'm adding a new service, I want to make sure there's at least circuit breakers added to it, right? And that kind of becomes part of the code review process. Becomes like a documented checklist that these things must be done, right? If I'm spinning up a new service, make sure there's a load balancer, make sure there's a load shedder, right? So basic stuff. As you get into the phase two, where you're kind of growing, and your P0 systems are becoming heavier, is where you will bring the formal phase, which is where I talked about Canary as a very lightweight use case, right? So even if you're not doing a formal resiliency review on every code review, right? Your design reviews start to become a little more sharper, right? They start to talk a little bit more about, hey, you're adding this dependency, what if it goes down, right? So those questions start to emerge in phase two. And the second is, of course, that in the canaries or those kind of phases is where you can then do fault injection. Now, endless possibilities, right? You can go as fancy as you like. My experience is, in reality, there's only probably like 5% companies out there who truly do them by the book. And I don't think everybody needs to do them, by the way, 100% either, right? So which is where just start by observing a handful of metrics, right? You typically know that you're a CPU bound service, right? Just run some synthetic traffic, do a shadow traffic, observe how much deviation, and that should generally get you set up for success. When it comes to formal events, like large scale events, is when you will definitely do a lot more rigorous resiliency as a phase, where, like I said, service audits. The one thing that I definitely encourage is periodic service audits, by the way, right? Regardless of what phase you are in. And this is a beautiful tool. Yes, it does take a lot from your committed goals. It does sound like a bit of a stretch. The organization starts to feel a little bit randomized, and people like really yank on it, like, why are we being made to do this? But you always get the value out of it. You always do. And the amount of training and coaching that you can give to junior engineers in that process is insane. So service audits probably is one thing that I would definitely recommend as a formal means. Please.
First of all, thank you so much, Harsh.
Sure.
Really very insightful, and the way you talked about it is very, very interesting.
Thank you.
Thank you so much for making it interesting also. The question I have is, in most of our customer discussion, we have been talking about shift left, which is about when you are doing the development.
Correct.
You also start making sure how are you going to observe this application, right? You do talk about like you are looking at different metrics and so on. What is your take on doing this sort of shift left when the development itself is happening? Do you suggest or do you do sort of bringing in observability or making sure that the application and infrastructure which you are selecting actually is observable through either open source products or OEM products, whichever way?
Sure. So little broad answer there. So I think for some core choices, absolutely. And this is where I think your paved paths ideology helps, right? So within the organization, I don't want to support N types of databases. I don't want to support N types of server frameworks. I would much rather have a few select. I would probably also have standardized libraries, right? Remember, like phase one we spoke about. You can use that as an opportunity to say, now I have a company-wide circuit breaker library that everybody must start to use, right? So you eliminate some of the choice paradox there and you bring standard practices, right? You also some part of it you also do in terms of, like I said, design review, right? Where in your design review template, you start to ask questions around simple stuff like, what if this component goes down? Is this also are you a P0 system? Is this dependency a P0 or not, right? So those kind of things. Beyond that, very, very candidly, if I were writing a book, I would say yes, do everything in shift left. If I were being pragmatic, I would say not possible, right? You're just going to hurt your deliverables. And I think I would do much rather emphasis on automation, testing, making sure functional stuff works, and very simple lightweight performance checks, right? Which you could do again, you could do as a part of the PR checks, or you could do in the Canario, whatever phase that works for you. I would start with them. If only they are being insufficient, is when I would really go back and say, oh no, this system has really outgrown, and I need to start thinking a lot more about its performance. Because again, context. What system are you talking about? What domain are you serving? If you are an AWS service, you cannot be launching without all of this having done ahead of time, right? But versus if you are, say, a product company, which is handling a certain number of users, maybe not something that you bother about every other day. So I think that is another lens that I would apply, but which is where for the largest amount of companies, I would imagine you would not bring a lot of this into the shift left, but you would do enough where you feel, yes, my P0 risks are at rest, right? So again, service audits, risk register to the rescue.
Thank you so much, Harsh. That was wonderful.